Hello, welcome to this new assignment. Today we're going to talk about anaerobic power assessment test. It's a comparative analysis of the wind gate, Margaria-Kelman, and force velocity profile. Why test anaerobic power? Because this helps as a performance prediction. It also helps you on training prescription and is the athlete monitoring. Also, you can do talent identification and you have a test selection criteria. The overview of the three complementary tests, we'll see that the wind gate test is anaerobic capacity on a 30-second cycle ergometer. Margaria-Kelman is an explosive power, is a stair sprint test, and the force velocity profile is basically a mechanical profile, sprinting or cycle based. The wind gate test protocol is a standardized 30-second cycle ergometer assessment. How you set up the test would be with a mechanical brake, monarch or electromechanical cycle ergometer, seat height adjusted at 5 to 10 degree knee flexion at max extension. The resistance load is for standard is 0.075 kilo per kilo body weight. It's around 7.5 body weight, 7.5% of the body weight. On athletes, like elite athletes, you can do 0.09 and 0.1. On a female and the general population, you do 0.075 to 0.085. How you execute the protocol is a standardized warm-up 3 to 5 minutes with 2 to 3 short sprints, then at 30 seconds all out maximal effort from start to finish. You have to do strong verbal encouragement and determination and safety. You complete that full 30 seconds regardless of fatigue. Active recovery is a cool down because it's essential to aid lactate clearance and prevent venous pooling. What are the key performances output? Here is the peak power, max at 5-second average. This would reflect the lactic capacity and explosive power. The mean power is the average over the 30 seconds all out. This reflects the anaerobic capacity and the glycolytic tolerance. The fatigue index would be peak power minus mean power divided by peak power times 100, and this is a percentage power drop off that indicates fatigue and fatigue resistance. And time to peak is seconds to reach the peak power. It's typically 3 to 5 seconds, measures the rate of force development. Here we can see that the contribution of the energy system is mostly glycolytic, and you have a peak lactate of 12 to 18 minimal minimal divided by liters, minimal liters. The physiology and fatigue mechanisms of power decline in the wind gate would be the PCR depletion kinetics, because there's a rapid decline, like 55 to 65% depleted of the PCR by the 10 seconds, and more than 90% at the end, which this is the primary driver of the initial power drop. The metabolic acidosis, there's a high glycolytic flux, leads to hydrogen ion accumulation. Muscle pH drops to 6.5 to 6.8, inhibiting the PFK and cross-bridge cycling. The lactate accumulation, the muscle lactate skyrockets, the blood lactate peaks, as we said, from around 12 to 18 minimal liter, 3 to 7 minutes post-test. And the performance determinants are the type 2 fiber area, the glycolytic enzyme activity, the phosphofructokinase and the lactodehydrogenase enzymes, and the buffering capacity that determines the fatigue index. Here, mostly is peripheral fatigue because the 80%, it's more than 80%, the dominant factor, which is the metabolic accumulation that inhibits contraction mechanics. And the central fatigue is mostly a secondary factor because the neural drive uh, re- reduces in the final 10 to 15 seconds due to sensory feedback. Here are the athlete profiles where there are the typical ranges. We can see here the sprint, the team, and the endurance athletes, and you see that the sprint usually and will have more peak power and would be on top of every measurement. One thing that is important to remember and to know is that a lower fatigue index isn't always better. It often indicates a lower peak power ceiling rather than superior endurance. Sprinters show massive drops because their initial output is extremely high, rapidly depleting finite PCR stores. That's why you see time fatigue index on the sprint athlete 50 to 65% drop, and on the endurance athlete you see 35 to 50% drop. The Margaria-Kalman test is a stair sprint protocol for peak lactic power. How you set up the test: you go to a standard staircase with 9 to 12 steps. Each step is approximately 17.5 to 20 centimeters high. Total vertical distance must be precisely measured. How is the approach and the ascent? You have a 6-meter sprint to build the velocity, and the athlete ascends 3 steps at a time. So there would be steps 3, 6, and 9 with maximal explosive effort. You use switch mats or photocells placed on the third and ninth step to measure time to cover the vertical displacement between these phases. And the duration basically is 0.35 to 0.55 seconds because it's pure lactic power assessment with negligible lactate accumulation. What are the key performance in here? The formula is power is mass times gravity times height divided by time. The peak power in watts is the absolute power. This is watts generated during the vertical displacement phase. The relative power is watts kilograms. It is a critical metric for comparing athletes of different masses. The vertical velocity is height time. The speed of vertical ascent is meters per second. And the energy system is basically ATP PCR, 90 to 95% of a lactic contribution. The characteristics of the test is basically an explosive neuromuscular performance because it's ATP PCR dominance. We already said is 90 to 95 percent of the energy contribution. There's minimal glycolytic contribution because the duration is not sufficient enough. Negligible acidosis. The lactate usually remains low, 2 to 4 millimole liter post-test. There's neuromuscular limitation. Performance basically is limited by neural drive, motor unit recruitment, and rate coding rather than metabolism. A difference of the Wingate test. You have a high transferability. There's a strong correlation with acceleration, change of direction, and vertical jump performance. Here we have the values and applications. You see that it has a higher transfer acceleration correlation with elite sprinters. Well, yeah, with elite sprinters because the explosive power that they need. is moderate to high transferability to team sports and very low transferability to endurance athletes. This helps you out in talent identification, the speed power phenotypes, the return to play for sprint readiness, and monitoring neuromuscular fatigue. Here we said that there's a strong correlation with short acceleration, uh, which makes these tests highly specific for assessing explosive first step, unlike the Wingate, which correlates better with sustained aerobic capacity. The force velocity profile, the biomechanical concepts and relationship. There's inverse linear relationship. As movement velocity increases, force production decreases, and that's a fundamental property of skeletal muscle. The theoretical max force, that's the theoretical maximum force an athlete could produce at zero velocities, indicator of max strength capabilities. The theoretical velocity max is the theoretical maximum velocity at zero load, and is an indicator of maximum neuromuscular contraction speed. And the actual versus optimal profile as a comparison, athletes' current force velocity slope against the optimal slope for maximizing power output in specific tasks. Its formula for maximal power is maximal force times maximal velocity divided by 4. The ratio of force is the percentage of total force directed horizontally, and is critical for sprint acceleration efficiency. That decrease in ratio of force is the rate at which horizontal force application effectiveness declines as speed increases. Flatter slope is better. The profile and testing protocols. The sprint-based protocol is how you set up. Is an indoors or constant surface, no wind, 30 to 40 meters distance is required, and the timing gates or radar gun laser systems is essential. The timing splits, the record splits times at 5, 10, 20, 30, and 40. Accuracy is critical for more model validity, which you need minimum of 5 data points. There's compute horizontal force velocity, ratio of force, and decrease of ratio in force using Samusino validated field method, which is a calculation model or calculated model. On a cycle-based protocol, you repeat sprints, perform 3 to 5 short maximal sprints, 6 to 10 seconds duration with full recovery, more than 3 minutes between the efforts. You do this at varied resistance. You use using different braking forces for each sprint, like 0.05, 0.075, 0.9, etc., to create force velocity spreads. The regression analysis, you plot peak velocity versus braking force for each trial. Linear regression drives maximal force intercept and velocity on the y-intercept, and max velocity on the x-intercept. Profile and key outputs here. The specific metrics, we already defined one. It's theoretical max force, theoretical max velocity, and peak mechanical power, maximal power, which is the apex power velocity curve calculated at, we said, maximal force times maximal velocity divided by 4, and represents explosive capability. And this is important to explain, which is force velocity imbalance, which is the percentage of the deviation from the optimal profile for a specific task used to identify force or velocity deficits. And the interpretation guide, low force suggests need for heavy resistance training as low velocity, max velocity suggests need for plyometrics over speed, and high force velocity imbalance, more than 10 or 15%, warrants targeted intervention to balance the profile. The interpretation and training for the force velocity imbalance. If you have a force deficient, the athlete generates insufficient force. What you do, the training focus will be on heavy strength training, more than 85% of the 1RM. You do heavy sled sprints, resisted jump squats, hill sprints. If the athlete is well balanced, the training focus would be on concurrent training stimuli, rise, maximal power, peak maximal power. You shift the entire core to the right. You maintain the force velocity ratio, and you do sport specific movements. If there's a velocity deficient, so the athlete is not speed enough, you focus your training on plyometrics over speed or assisted sprinting, light sled sprints, less than 10% of body weight, and ballistic movements. The sprint distance optimization, the optimal profile shift based on distance. Shorter sprints, 0 to 10 meters, require more force bias, as longer sprints, more than 10 meters, require more velocity bias. How you use this on the periodization strategy? You use periodic testing every 4 to 6 weeks to monitor shifts in force velocity slope and adjust training loads modalities to prevent overcorrection. Here is basically a comparison of the system dominance in each test. You see the Wingate is basically high stress metabolic test with severe PCR depletion. The Margaria-Kellman is pure lactic power, less than 15% depletion of the PCR, ATP PCR system, and the force velocity profile is the energy system is basically mechanical. So Wingate test is mixed lactic and alactic. Margaria-Kellman is pure lactic, and force velocity is much more mechanical. Basically, a profile comparison, sprint power, the Margaria-Kellman, and the Wingate. The performance patterns, force dominant, exceptional early phase acceleration, and pure lactic power, massive force velocity power max, but rapid fatigue due to fast twitch fiber reliance. The team sports, it's basically the performance pattern is a balanced profile. You have strong neuromuscular output with moderate anaerobic capacity. The force velocity profiles well often balanced, essential for repeated sprintability. And the endurance is low peak mechanical power, but superior fatigue resistance. The comparative analysis, a pure sprinter excels in Margaria and force velocity, but shows step decline in Wingate. Endurance athletes shows the inverse pattern, lower peaks, but flatter fatigue curves, reflecting metabolic efficiency and raw power. Practical application test selection. You start the assessment if you're looking for explosive power and acceleration. Margaria-Kellman, you look for anaerobic capacity and lactic tolerance. Wingate, mechanical profiling and individualization. You use force velocity. Return to play and monitoring. Hybrid approach. The primary use for safe power checks and periodic force velocity profile, as the Margaria-Kellman, as we said, is for safe power check. Implications by tests. This is basically a repetition of what we already said. Wingate test, anaerobic capacity, prescription is lactic power, 6 to 10 seconds all out with longer rest. If you look for lactic capacity, 20 to 40 seconds repetitions with incomplete rest. The tolerance is repeated sprints with short recovery, buffering. For buffering, you prescribe high intensity interval training. The Margaria-Kellman principal main focus is explosive power. For max strength, heavy squat deadlifts more than 85% of the 1RM. Rate of force developments, you use Olympic lifts, plyometrics, and sprint, like short hill sprints, and the force velocity profile. If you have a force deficit, you can use heavy sled, push, pull, heavy resistance, velocity deficit. You use assisted sprinting, light sled, span work. For progression, you use force velocity imbalance set at percentage of body weight. Optimization tailor to sport specific distance needed. So the load and load management and volume. You can use the force velocity imbalance metric to precisely prescribe sled loads and manage total volume based on neural fatigue. Progression model, shift focus periodically from general strength to specific power qualities based on retesting results every 4 to 6 weeks. Here is basically a summary feature by feature comparison. We already basically saw everything. We haven't saw or talked about the pros and the cons. Pro of the Wingate is a gold standard valid for anaerobic capacity. The Margaria-Kellman, the pro is explosiveness, direct lower limb power measure, force velocity individualization because identifies force and velocity deficits. The cons of the Wingate, really high metabolic stress, can cause nausea, high fatigue, long recovery. The Margaria-Kellman, you need there's a real skill factor in the test, time and accuracy coordination, and force velocity. There's assumption relies on linear model validity. And here are the references that I use for this test, test comparison and this assignment. So thank you very much.